Hi, I am Gunjan Dhanuka, and this is our video presentation on distilling aggregated knowledge for weakly supervised video anomaly detection. In this work, first we show that knowledge transfer plays an important role in weakly supervised video anomaly detection due to limited supervision present during training. Then we propose a novel temporal aggregation module to combine knowledge from multiple backbones. Finally, we perform spatio-temporal knowledge distillation to distill knowledge from multi-backbone teacher into a single backbone student, making inference more efficient. Here is a broad overview of our method. First, we divide the video into segments and then extract the features for the videos using different feature backbones indicated by F. Then, to aggregate the features, we use the temporal aggregation module, which is explained in detail in the next slide. We use the multiple instance learning ranking approach proposed by Sultani et al. For training the teacher model, and then refine the obtained predictions to use them as pseudo labels for the student model. Then, we employ distillation to overcome the computational overhead of multiple backbones and perform distillation at two levels, feature level and prediction level. Since anomalous actions in the natural world exhibit low pass temporal frequency and tend to cluster together rather than being spread among normal observations, we use the relative positional information to enhance anomaly detection performance. Here, C1 and C2 correspond to two feature representation obtained from the backbones, and Q, K, and V are query key and value vectors obtained from the TS backbone. QR and KR are relative position based vectors. We compute four attention matrices for each backbone, and these are then aggregated across the backbones to give the final output H. The architecture of the temporal aggregation module integrates the disentangle attention mechanism to improve the relative encoding and fusing of representations from multiple backbones. Here is a formulation of our aggregation. Gamma is defined as the relative distance between position I and j and is constrained in the interval 0 to 2k, which reduces the complexity of the attention model and makes it suitable for low data and weak supervision settings. Our disentangle attention has three components: content to content, which attends to the content of a token at position I by interacting with the content of the position at token j within the same sequence. Then we have content to position, which considers the content of token I and its relative position to token j, capturing how the content of token I influences its attention weight concerning token j. Position to content is very similar, which this component assesses the content of token j and its relative position to token I. And then finally, we add a cross attention module to fuse information from multiple input sequences. This is the formulation for our distillation approach. We use the teacher's segment level predictions to provide robust learning signals. These predictions act as soft pseudo labels for training the student model. Since we are certain about the segment level annotation for normal videos, we can combine the soft anomaly labels with normal videos. In feature level distillation, we utilize a multi-layer perceptron with a single layer to transform the input representations Hi from both the student and the teacher models into corresponding feature vectors Z. Then we use a threshold to identify four distinct feature subsets: ZTA, which are the anomaly features of the teacher; ZTN, which are the normal features of the teacher; ZSA, anomaly features of the student; and ZSN, normal features of the student. Here, in the distillation loss, tau is the temperature parameter and alpha represents the scaling coefficient to control the contribution of the two loss terms. These are the datasets on which we train and evaluate our method, which are UCF crime, Shanghai Tech, and XD violence. On the UCF crime dataset, our method outperforms the current state-of-the-art methods. It is also very efficient since it does not use multi-scale video crops for training. Also, our method achieves an AUC score of 98.1 on the Shanghai Tech dataset, which is superior to previous methods, although performance on this dataset looks to be saturated. Our method also receives an AP score of 85.61 on the XD violence datasets and outperforms existing method by a significant margin. When investigating the impact of knowledge transfer from feature backbones, it is evident that clipped backbone consistently outperforms other combinations. Moreover, the combination involving all three backbones yields the best performance and is consequently adopted for training the teacher model. We also compare the impact of various key components of our framework, like temporal aggregation module, bi-level distillation objective, and the pseudo-level refinement. The results show that each component is important and all the components are crucial towards achieving optimal performance. We can also see that the proposed temporal aggregation module outperforms other popular temporal networks in terms of the AUC score on UCF crime. Notably, temporal aggregation module also outperforms vanilla disentangle attention and multi-head attention mechanisms, showing its efficacy. Here are the qualitative results from our work. Finally, we conclude that in this work, we introduced a novel method, DAKD, to tackle weakly supervised video anomaly detection. We propose a temporal aggregation module to merge diverse representations from multiple backbones via disentangle cross attention. We reduce the computational cost through a bi-level knowledge distillation process, transferring knowledge from the aggregated model to a single backbone student. Finally, we achieved state-of-the-art performance in weakly supervised VAD, with the student model outperforming existing state-of-the-art methods. Here are the references that we uh, referred to in this talk. Thank you.